Hello, so the next part I will finish the chapter 4 and share my screen with you so we can finish that part together. So the first one is file input and output with the arrays. So we can use np.save and npload to save and load array data on disk and load it back. So that's how we do it. We save one and we load it back. I'll remember the file need to end in .mpy. Then we save multiple arrays in an compressed archive using np.savez and passing the array as keyword arguments. Okay, so what should we do here is let's save it with save z and archive array, then a a equals to ar b r. Okay, we don't have. So right now we save multi arrays in this archive. Um, and so if we want to load it back, then right now is not mpy, it is mpz. So we load that back and archive. Then within it, I'm very curious. Okay, we cannot see anything there, but okay, is A. This is A, and we can also extract B. So if my data compresses well, I wish to use numpy.saves compressed instead. So only difference, oops, sorry, only difference here is 2. Okay, what I want is this. Saves compress. And then we load it back by np.load, np.load, mpz, mpz, and what do we get right now? It is okay. So next step we will talk about is linear algebra. So linear algebra, like matrix multiplication, decompositions, determinants, and other square matrix math, is an important part of any array library. Unlike some languages, so multiplying two-dimensional arrays with a star is an element-wise product instead of a matrix dot product. Therefore, there is a function dot, both an array method and a function in a NumPy namespace. So if you know anything about linear algebra, so you want to multiply two matrix together, then in NumPy you need to use dot. So okay, I will create two array here, which is array, and then 1, 2, 3, and 4, 5, 6. And then we go to say y np array 3, 5, 6, and okay, np dot array. This is x and this is y. Okay, I lost a bracket here, right? So I lost the bracket here. And then what we will check is x dot y. So that is the result. And we can also do is np dot x y. So the results are the same. The matrix product between a two-dimensional array and a suitably sized one-dimensional array results in one-dimensional array. So yeah, I think that is some technology you should know from linear algebra. So I will not talk so much about it here. The next thing I want to talk about actually is the NumPy linear LINALG. It has a standard set of matrix decompositions and things like inverse and determinant. So these are implemented under the hood via the same industry standard linear algebra libraries used in other languages like Matplotlib and R. So what should we do with this package? Here is an example. So first we need to from numpy dot main import inv qr these two method, and then okay, we have a new, I need to create a new array which is random run dn or run dn and 5 5. So this is what I created. I created a new array again. So in this array, first we do a transpose and what we do is to use it to multiply itself. So here is the result, and then we will use okay T is equal, this is a matrix, so we will use okay and I also use the net dot inv. Actually it's inverse, I think. Yeah, because use the original matrix to multiply your inverse inverse matrix. Then okay, it seems like number is not, actually it should be a diagonal matrix, and where only the unique value is 0 and 1. So here are some problems. Maybe let me rerun it to see. So here is x that is correct, and s is np dot random, right? And then we have mat, which is x dot t dot, let me use the dot function ret t, and then we get the inverse and mat dot. Okay, so why we have this result? So the only thing I can think about is that maybe this number is too small, or that we can think it is 0. And the next thing that we look at is, okay, q dot r. Q dot r is equal to qr mat, right? So what is r? What is r? So the expression x dot t dot x computes the dot product of x with its transpose x dot t. Yeah, that's correct. So what should we do with QR? QR is to compute the QR decomposition, and okay, what is QR numpy lin ALG numpy, which is lin ALG, and QR. What is QR? Is so factor the matrix A as QR, where Q is orthonormal and R is upper triangular. So let's go to check the next part, is pseudo-random number generation. So the NumPy random module supplements a built-in Python random with functions for efficiently generating whole arrays of sample values from many kinds of probability distributions. Let's check the sample. Okay, so actually it means that we can create some random, like, normal distribution data. So in this data set, or in this array, we can get a 4 multiply 4 array of samples from the standard normal distribution. And the next thing about random is that, so only samples one value at a time. So as you can see from the benchmark, NumPy random is actually it's better than an order of magnitude faster for generating very large samples. So how to understand this, let me show you from random. Import normal y rate, right? And then what we want to have is, okay, n is equal to this number, and So the next part is to look at, okay, I want some time. 10 8 samples is equal to normal variate 0, 1, and 4, and okay, it spends us, this is the time we spent to finish this part, and then we change another range, np.random.normal, np.normal, and size is equal to, and wow, so it's much quicker, right? So we say that these are pseudo-random numbers because they are generated by an algorithm with a deterministic behavior based on a seed of random number generator. You can change NumPy's random number generation seed using np.random.seed. Okay, yeah. So which is like this seed. So you can input a number here. And the data generation functions in NumPy random use a global random seed. To avoid a global state, you can use NumPy random state to create a random number generator isolated from others. So the RNG can be NP random state, 1 2 3 4. Then you can use this one, this RNG, to create random values. So we have actually a lot of functions available in numpy.random, and which you can create any actually distributions you would like. So the last part, whoa, we are going to the last part of of NumPy basics. That's great. So the last part is random walks. So what is random walks is that the simulation of random walks provides an illustrative application of utilizing array operations. And so for this walk, so we can check in Python that how to implement a single random walk with 1000 steps using the built-in random module. So we import random, and then position equal to 0, and the walk is equal to position, right? Position, okay. And then the steps will be 1000, and for I in range steps, we do for next is step is equal to 1 if random dot rand nt 0 1 else -1, and then position is equal to step and walk dot append. Let's check what's in walk, okay? Wow, so there are numbers here in precision, and so let's plot what we have, okay? And if we want to plot what we have, the first thing is that we need to import matplotlib pyplot as plt, right? So right now we will plt dot plot and walk. Okay, this is what we get, and so the walk is the cumulative comp sum of random steps and could be evaluated as an array expression, right? So we can use the np.random module to draw 1,000 coin flips at once, set these to 1 and -1 and compute the comp sum. And so this is then in this way we can get the walks minimum and maximum and mean like that. So that's how we create random walk, use random walk to create data set. So a more complicated statistic is the first crossing time, the step at which the random walk reaches a particular value. So here we want to know how long it took the random walk to get at least 10 steps away from the original 0 in either direction. So np.abs walk, which is bigger than 10, gives us a Boolean array indicating where the walk has reached or exceeded 10, but we want the index of the first 10 or -10. Turns out we can compute this using argmax, which returns the first index of the maximum value in a Boolean array. So how to understand this? That's okay. I can use np.ab np.abs walk is bigger than or equal to 10. There are 22 of them there. So using argmax is not always efficient because it always makes a full scan of array. In this special case, once a true is observed, we know it to be the maximum value. Okay, kind of confused here, so let me check the documents. Okay, let me check the documents to return the indices of maximum values along an axis. Right, so in this A, then we will return the indices, right? So which one is the largest? Okay, so if you compare like this, 10 and 13, so 13 is the larger one. So here we get the index of it. Because this is 0, this is 1, the index So, okay, I'm kind of understanding this. And so let's go to the next one, which is simulating many random walks at once. So if our goal is to simulate many random walks, maybe like 500,000 of them, we can generate all of the random walks with minor modifications to the preceding code. If passed a two-tuple, the NumPy random function will generate a two-dimensional array of jaws. We can compute CumSum across the rows to compute all 5,000 random walks in one shot. So how to understand this? Let me check. So what we can do is, okay, right now n walks is equal to 5,000 and n steps 1,000 and jaw is equal to np dot random int 0 1 size equal to okay n blocks and n steps. Then what we have, okay, ends here, and we will go to the next step. Is steps is equal to np dot where, and jaws is larger than 0, and 1 minus 1. And these are the steps, and the walks equals steps dot CumSum 1. So let's see what's in walks. Okay. So now we can compute the maximum and minimum values obtained over all of the walks. So walk, I actually want to know how large is this walks. Okay, 500. And also what is the length for each of your walks element? Okay, it's 1,000. So we can do walks dot minimum, walks dot min, right? We can do a lot of things you want. So let's compute the minimum crossing time to 30 or negative 30. Okay, we can use method which is, okay, paste 30 is equal to np dot absolute walk is larger than or equal to 30 and the dot any. Okay, where the problem is, okay, walks. We have walks and paste 30 and here's the 30 sum up together. Okay, because what we want, we can use this Boolean array to select out the rows of walks that actually cross the absolute 30 level and call argmax cross across axis 1 to get the crossing times. So, so what should we do is like this. We have crossing times, which is equal to np dot array, np.abs walks is 30 and argmax 1. So browsing times. So this is browsing times, and we compute the average minimum browsing time, which is mean. Okay, so I mean, so that's all for this chapter, and well, much of the rest of the book will focus on data wrangling skills with pandas, but um, we will continue to work on array-based style. So let's go to the next chapter, or so, which is the one that I'm most familiar with. Py, pandas package. That's it for chapter 4. So let's meet in the next video.